In this lesson, let's just find some more Taylor and Maclaurin series based on some of the ones that we know, and let's also talk about how Maclaurin and Taylor series can be used to integrate, find limits, and approximate functions. So first of all, the definition of Maclaurin series for a function f of x is a series of the form f of 0 plus f prime of 0 times x plus the second derivative at 0 divided by 2 factorial times x squared, plus the third derivative at 0 over 3 factorial x to the third, etc. Or in summation notation, it's a sum from n equals 0 to infinity, the nth derivative at 0 divided by n factorial multiplied by x to the n. So let's find the Maclaurin series for sine of 5x using the definition. You could have also used the Maclaurin series for sine of x and inputted 5x for x. We can do it at the end to verify that our series matches. So first of all, f of x is sine of 5x. The derivative of sine of 5x is 5 cosine of 5x. And the second derivative will be negative 5 squared sine 5x, and the third derivative will be negative 5 cubed cosine 5x. And after this, the cosine and sine portion of the derivatives are going to cycle, and the power on the 5 matches the numberth derivative that you have. So notice that f of 0 is 0, f prime of 0 is 5, the second derivative at 0 is 0, the third derivative at 0 is negative 5 to the third. So by definition, the Maclaurin series f of x is f of 0 plus f prime of 0 times x plus the second derivative at 0 over 2 factorial x squared, etc. So f of 0 is 0, f prime of 0 is 5, so we'll have 5x. The second derivative is 0, so that 0 is at the next term. And then the next term that we have is the cubic term, where we'll have negative 5 to the third x to the third over 3 factorial. And then the next one we'll have will be 5 to the fifth x to the fifth over 5 factorial, etc. So that's 5 minus 5 to the third x to the third over 3 factorial plus 5 to the fifth x to the fifth over 5 factorial minus plus their flip-flop, etc. Written in summation notation form, it's a sum from 0 to infinity, negative 1 to the n, 5 to the 2n plus 1, x to the 2n plus 1, all over 2n plus 1 factorial. And that's the same thing as if we would have gotten if we would have taken the series, the Maclaurin series for sine of x, which is this. And we would have input 5x there instead of x, and that would give us the exact same series. A Maclaurin series is a special case of a Taylor series. So a Maclaurin series is centered at the point x equals 0. Taylor series are centered at the point x equals c, so any particular value. And the Taylor series is given by the series f of c plus f prime of c times x minus c plus the second derivative at c over 2 factorial multiplied by x minus c squared. The nth term is given by the nth derivative at c over n factorial x minus c to the n, etc. Or in summation notation, it's a sum from 0 to infinity. The nth derivative at c over n factorial multiplied by x minus c to the n. So let's find a Taylor series for the function 1 over x centered at a equals 3 using the definition. This could also be accomplished using manipulations and a geometric series. So f of x is 1x to the negative first. The first derivative will be given by negative 1x to the negative 2. The second derivative is positive 2x to the negative 3. The third derivative will be negative 6x to the negative 4th. The fourth derivative is positive 24x to the negative 5th. What you could also notice is that 24 actually is 4 factorial, 6 is 3 factorial, 2 is 2 factorial. Alright, so now the Taylor series for f of x is going to be given by f of 3 plus f prime of 3 times x minus 3 plus the second derivative at 3 over 2 factorial x minus 3 squared, etc. More terms, we'll add those on as we go on, dot dot dot. So f of 3 will be 1/3. F prime of 3 will be negative 1 over 3 squared times x minus 3. The second derivative at 3 will be 2 over 3 to the third multiplied by 1 over 2 factorial, x minus 3 squared. And just to get another term in there, next we'll have the third derivative at 3, so that will be negative 6 over 3 to the fourth multiplied by 1 over 3 factorial, x minus 3 to the third, etc. Now notice that this 2 and 2 factorial will cancel, the 6 and 3 factorial will cancel, in the next term the 24 and 4 factorial will cancel, and that leaves us with a third minus 1 over 3 squared x minus 3 plus 1 over 3 to the third x minus 3 to the second plus 1 over 3 to the fourth x minus 3 to the third. So written in summation notation, 0 to infinity, negative 1 to the n because of the alternating nature of the series. If we have x minus 3 to the n, so notice that when the power is 1 on the x minus 3, the power on the denominator's 3 is actually 1 greater. So the denominator will have to have 3 to the power of n plus 1. So here we have a list of all the Maclaurin series that are pretty commonly used. So 1 over 1 minus x we found using a geometric sum. Recall that this had radius of convergence r equals 1. Expanded out, this would look like 1 plus x squared plus x cubed, etc. E to the x we found in this section. So that series expanded out looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. It has radius of convergence infinity. Sine x is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Also has an infinite radius of convergence. Cosines series can be found by differentiating signs. That would give us 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. Also has an infinite radius of convergence. inverse tangents Maclaurin series we found in a previous section using a manipulation of the geometric series and integration. This is given by alternating, and the first term is x. So x minus x cubed over 3, notice no factorial, plus x to the 5 over 5, still no factorial, minus x to the 7th over 7, etc. It has radius of convergence 1. And then the last one is the expansion for 1 plus x to the k. Now this k over n with parentheses notation is read k choose n. And that is a fancy way of writing down what these coefficients would look like. So here's the expanded form for that in case you forgot. It's 1 plus kx plus k times k minus 1 over 2 factorial times x squared plus k minus 1, k minus 2 over 3 factorial x cubed, etc. And that has radius of convergence 1 also. Next, let's use those to find Maclaurin series for related functions. So for this one, we're going to use the Maclaurin series for e to the x, which is a sum from 0 to infinity, x to the n over n factorial, and we will input negative x squared for x. So this is equal to the sum from 0 to infinity, negative x squared to the n over n factorial. And a slightly more proper way to write that would be to pull out the negative 1 to the n and write it as x to the 2n over n factorial. If we have x cosine x, I can find the Maclaurin series for cosine x and then multiply that by x. So the Maclaurin series for cosine x is the sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. When that x enters the sum, it will multiply by the x to the 2n. And notice that x to the 2n times x to the first is the same thing as x to the 2n plus 1, all over 2n factorial. Here we have one of these semi-tricky binomial ones. So first express this as 1 plus x to the negative 5th. So the binomial expansion for 1 plus x to the k is given by 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k minus 1, k minus 2 over 3 factorial x cubed, etc. So with our particular example, we have k equals negative 5. So 1 plus x to the negative 5th will be 1 minus 5x plus negative 5 times negative 6 over 2 factorial x squared plus negative 5 times negative 6 times negative 7 over 3 factorial x cubed, etc. So that will be 1 minus 5x plus 5 times 6 over 2 factorial x squared minus 5 times 6 times 7 over 3 factorial x cubed. If you want to cancel anything, it's completely up to you. I don't think there's any convention for what is or is not done. Sometimes not canceling things makes it easier to see patterns. And we have e to the x added to 2e to the negative x. So e to the x has Maclaurin series n equals 0 to infinity x to the n over n factorial plus 2 times the series 0 to infinity negative x to the n over n factorial. So 0 to infinity x to the n over n factorial plus 2, and taking out the negative 1, we'll have negative 1 to the n x to the n over n factorial, which can be expressed as one sum. So from this first term we'll have 1, second term we'll have 2 times negative 1 to the power of n, all multiplied by x to the n over n factorial. One useful application is to use a Taylor series to integrate a function. So if you have a function for which you cannot find an antiderivative, you could find or estimate the area under the curve by finding an expansion of the function and integrating term by term and using this as an estimate, and then using some kind of alternating series test to estimate your error. So for example, if I want to find the integral from 0 to 1 of e to the negative x squared, there are no techniques that you know of, or probably at all, to antidifferentiate this function and get an antiderivative. So we have to resort to estimation techniques. And instead of using the whole boxes under the curve approximation technique, let's use the series technique. So first of all, e to the negative x squared can be expressed as a sum from 0 to infinity, negative x squared to the n over n factorial, or a sum from 0 to infinity, negative 1 to the n, x to the 2n over n factorial. So now suppose we want to find the antiderivative of e to the negative x squared. Can't do that, but I can antidifferentiate this series, just term by term, and that will work as long as you have a convergence series, which with this has radius of convergence infinity. So negative 1 to the n, x to the 2n over n factorial. When we antidifferentiate, it will be a sum from 0 to infinity, still negative 1 to the n, but now it's x to the 2n plus 1 over 2n plus 1 multiplied by n factorial. And now if I wanted to find the integral from 0 to 1, I can take that series and evaluate it from at 0 and at 1 and subtract the difference. Now notice putting in 0 will yield 0 because all the terms will have 0 to some power, zeroing them all completely. Inputting 1 for x will have 1 to the 2n plus 1. So that will be the sum from n equals 0 to infinity, negative 1 to the n, 1 over 2n plus 1 times n factorial, which converges by the alternating series test. Even though we can't find that sum exactly, we can still estimate it. So we have the sum from 0 to infinity, negative 1 to the n, 1 over n factorial 2n plus 1. So we know from the alternating series test remainder that the absolute value of the error is less than or equal to the n plus first term, or the absolute value of the n plus first term. So we want the error to be less than 0.001. So 1/1000th, 1 over n plus 1 factorial. Now when I input 1 there, I'll have 2n plus 1 plus 1, which is 2n plus 3. And now you just test n's until you get one that works. It is best to use the smallest n that works, and the smallest n that works is n equals 4. When you input n equals 4, this expression is about equal to 0.000757. So that's the first time your error drops below 0.001. In some ways, it's pretty remarkable that just adding up 4 terms of that series gets you a pretty darn accurate estimate of what the integral's value is. And I suspect that for some calculators, this is actually how they generate decimal expansions or estimations of what an area is under a curve. They probably find a power series, and they figure out what accuracy is needed, and they add together a certain number of terms. Perhaps. They might also use a Riemann sum of some sorts. Alright, let's evaluate the integral of x cosine x cubed. So, and I'd like just to give your answer as a sum. So we have, this is equal to x times the sum from 0 to infinity, negative 1 to the n, x cubed to the power of 2n, all over 2n factorial. That's the same thing as the integral from, and the integral of the sum from 0 to infinity, negative 1 to the n, x to the 6n plus 1 over 2n factorial. And that can be given by sum from 0 to infinity, negative 1 to the n, x to the 6n plus 2, all over 6n plus 2 times 2n factorial. Technically, this swapping of the integral and the summation relies on your series being a convergent series in the first place, which this is because the radius of convergence was infinite. Now, a series could also be used to evaluate limits. Notice also that for this limit you could use L'Hopital's rule since it is of the form 0 over 0. But just to show you how a series could be used, let's do it that way. We can use L'Hopital's rule to verify that this actually worked. So the limit as x goes to 0, the expansion for e of the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And then minus 1 minus x all over x squared. So the 1 cancels, the x cancels, and we have the limit as x goes to 0 of x squared over 2 factorial plus x cubed over 3 factorial, etc., all divided by x squared. And we divide each term by x squared. We'll have 1 over 2 factorial plus x over 3 factorial. Next we would have x squared over 4 factorial. So every single term past this point has an x. So now we can input x equals 0 into all these terms, and every single term will be 0, except for the 1 over 2 factorial, which is 1/2. So that limit is 1/2. Alternatively, if you wanted to use L'Hopital's rule, you differentiate the numerator and denominator, and you can use this because it is of the form 0 over 0. So we'll have e to the x minus 1 over 2x, and we still have the form 0 over 0. Use L'Hopital's rule again, and we end up with e to the x over 2. And now when you input 0, you have that this limit is 1/2. So same thing either way, it's just the point that the series can also be used. Final thing we're going to do with these series are multiply them and divide them, and multiplication and division are tedious enough when you have finite polynomials, let alone infinite series. So this can get a little bit ugly. So if we're taking e to the x times cosine x, so first of all, e to the x's expansion is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. We're only looking for the first 3 non-zero terms, so that's probably going to be enough. And then with cosine, we'll have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then minus x to the 6th over 6 factorial, etc. Alright, now first I'm going to distribute the 1. So if I do the 1 times the 1, I'll have 1. And I'm going to leave some space here, like a space for the x's, minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then minus x to the 6th over 6 factorial. So that's the 1. Now I distribute the x. X times 1 will give me plus x, times the x squared would be minus x cubed over 2 factorial, times the x to the 4th would be plus x to the 5th over 5 factorial, etc. Then if I distribute the x squared over 2 factorial, that multiplied by the 1 gives me positive x squared over 2 factorial, multiplied by the x squared over 2 factorial will give me negative x to the 4th over 2 factorial squared, and multiplying this by the x to the 4th will give me a positive x to the 6th over 2 factorial times 4 factorial. And I think if we just do the x to the 3rd now, we'll be pretty good. X to the 3rd times 1 would be plus x to the 3rd over 2 factorial times 3 factorial. And then we'll have minus x to the 5th over, that first x to the 3rd should just be x to the 3rd over 3 factorial because that was multiplied by 1. And then minus x to the 5th, 3 factorial, 2 factorial. As you can see, because it gets really awful really fast. So first of all, the 1 doesn't cancel. 1, neither does the x. But the x squareds do. But the x to the 3rds do not. So that's the 3rd term that I care about. And everybody else's power is going to be bigger than 3, so it doesn't actually matter all that much. So I'm going to add together this negative x to the 3rd over 2 factorial and that x to the 3rd over 3 factorial. So that's negative x cubed over 2 plus x cubed over 6, which is the same thing as negative 3x cubed over 6 plus x cubed over 6, which is negative 2x squared over 6 or negative x cubed over 3. There's the first 3 non-zero terms. And lastly, division. So find the first non-3-zero terms in the Maclaurin series for f of x equals tangent of x. And what you'll have to remember is that tangent is equal to sine over cosine. So we're going to take the series for sine, which is x minus 1/3 x cubed plus 1 over 5 factorial x to the 5th minus etc. all over 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, etc. We're going to divide those. Egads. Okay, so 1 minus 2, 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, etc. going into x minus 1 over 3 factorial x to the 3rd. It's actually best now to write those as real number as well. Multiply them out, so that's 1/6 x to the 3rd plus 1/20 x to the 5th minus etc. So you have to think about what do you multiply the 1 by to make it match x, and that's going to be x. So x times 1 will be x. X times 1 over 2 factorial x squared will be minus 1/2 x to the 3rd. And then you subtract that. Doing 1/6 minus negative 1/2 actually ends up adding 3/626. That's going to be 1/3 x to the 3rd. And then the 1/20 x to the 5th comes down. And then you think, what do you multiply this by to make it match 1/6 x to the 3rd? It's going to be positive 1/3 x. So that will give us 1/3 x to the 3rd. So it'll give us 1/3 x to the 3rd minus 1/6 x to the 5th. Take that away. And what we have is 2/15 x to the 5th. So to multiplying 1 by 2/15 x to the 5th, we'll do it, and there's your first three terms. Often the first terms are the most important, so that's the ones we're going to find. Just very, 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 very tedious process here.